about surface codes with Kerr-cat qubits. So go ahead and take it away, Shruti.
So you can see my slides?
Yes, we can see your slides.
And my pointer?
Yes, yes,
Great.
all the good.
Great, so I'm very excited to virtually be in Australia. So I decided to change my background for the talk. And this is a Google image of a beach in Byron Bay. So I was supposed to be there last year, but well, that didn't work out. Okay, so today I am going to talk about surface codes with Kerr-cat qubits. So Kerr-cat qubits was something that we've been working on for a few years now. The idea, the theoretical idea was started in Alexander's group, and we've continued working on it and at Yale with lots of collaborators. And today, the results, some of the numerical results that I'm going to show you is in collaboration with these guys at Sydney and Kyoto. So special thanks to David, Ben, and Arne, and also to Andrew. So a lot of the simulation results that I'm showing now is based on the code that Andrew wrote. This work, we were able to carry out this theoretical work because of the hard work also from the experimentalists in Michel Deveray's group, so Alex and Nick, who demonstrated the first Kerr-cat, experimentally determined their noise properties and gates, etc. I think you heard from Alex last year at Byron Bay, and you'll hear from Nick today just after my talk. You'll hear about the new updates on the Kerr-cat and how you do, a special gate in those with the Kerr-cat qubit. Okay, so there's going to be two main messages for my talk, in my talk. The first message is know your noise. For a long time, we have been using fidelity as a sole metric to characterize how good or bad your qubit is or how good or bad your gates are. However, what we have realized is that fidelity is not the only metric. The structure of the noise or the bias in the noise is equally important. So if you have two qubit architectures which have exactly the same total infidelity or same total fidelity for the different operations, but in one qubit architecture, if the noise is such that the way it occurs has some structure to it, that qubit platform is going to be much more preferable than the other one in which has the same fidelity, but the noise has no structure. The noise has no underlying structure, which we can exploit for quantum error correction. The second main message is fault tolerance with bosonic qubits. So there is, there have been a lot of arguments that it's not really clear how you would scale up these bosonic qubits for full fault tolerance, but you'll see that you can achieve full fault tolerance with bosonic qubits. And not only that, there's an advantage that the error correction actually becomes more efficient if you exploit the underlying properties of these continuous variable qubits. So with that, we'll come to the outline of the talk. So firstly, I'll introduce the basics. We'll look at what I mean by structured noise. We'll look at surface codes for structured noise. Then I'll tell you what the Kerr-cat qubit is. And then I'll tell you how you can improve the surface codes with the Kerr-cat qubit. Okay, so the first part. In a quantum system, we can decompose errors into three types. So you can have a bit flip error, which is like the action of poly X operator on your state. So 0 goes to 1, 1 goes to 0. And then you have the phase errors, which is the action of poly Z operator on your state. So it messes up the phase information. And then there's a Y error, which is like the action of both poly X and poly Z operator on your state. The most commonly studied noise model is a depolarizing noise model, in which you assume that all these three errors happen with equal probability. So the probability of a Z error is the same as the probability of an X error, is the same as the probability of Y error. However, there are many qubit platforms in which the noise is biased. That is, one noise is more common than the other noise. So we will look at a particular qubit in which the probability of Z errors is more likely than the probability of X and Y error. So in these qubits, along with the total error, which is px plus py plus pz, it becomes important to define another quantity called as the bias, which is the ratio of the probability of a z error and the probability of x and y errors. Okay, so now let's see how one would imagine doing error correction to correct for all these three types of errors. So one of the, as everybody knows, one of the most popular error correcting codes out there is a surface code. The surface code is nice because it requires only 2D, a 2D lattice of qubits. And you have you have two stabilizers in the surface code. You have the X stabilizer and the Z stabilizer. So the X stabilizer is a 4-body X operator acting on the 4 qubits around the blue plaquettes, and the Z stabilizer is a 4-body Z operator acting on the 4 qubits around the red plaquettes, and at the edges you have the 2-body operators. So with these, so if there are no errors, if you measure these stabilizers, the measurement results will be +1. But if there are errors, if there's a Z error, then the X stabilizer will tell you about it because it will become -1. And if there's a X error, the Z stabilizer will become -1 and tell you about the error. Now, the size of the lattice for the surface code depends on how many number of errors you would like to correct. So if the number of errors you want to correct is n, and if the physical error rate or the error rate per gate operation or per time step is p, and if you assume a depolarizing noise model, then the probability of a logical error or the failure rate of this logical qubit depends on p and p threshold by this formula, and n is basically related to the size of the lattice. So as long as p is below p threshold, you can increase n and reach as small a logical error rate as you want. So the threshold for this regular surface code is about 1%. So say if you want to factor a 2000-bit number, then you're looking at target logical error rates of about 10 to the -12. So if you want if p, the physical error rate in your lattice, is about 0.1%, then you can put the numbers in this formula and extract that you need n of about 12, which means you need a lattice of about 625 data qubits. Now, if you so say you were magically able to increase the threshold by a factor of 2, then now for the same parameters, for the same p and same n, you'll be able to get to much lower logical error rates. And now you'll be able to tackle much bigger problems like finding the ground state of this, big FOMOCO molecule, which is used for nitrogen fixation. So even because of this exponential suppression and errors, even a factor of 2 increase in the threshold is going to buy you a lot in terms of hardware that you require to reach particular logical error rates. Okay, so now very recently people have, especially the guys at Sydney basically, have designed new types of surface code which are tailored for bias noise qubits. And actually a very, very recent work came out, which was this so-called XZZX surface code. So unlike the previous case where you had 2 types of stabilizers, here you just have one stabilizer, which is this 4-body XZZX operator acting on the 4 qubits around each of these plaquettes. And of course, at the boundary, you're going to have the 2-body operators. Now, if you wanted to say measure the value of these stabilizers, what you're going to do is you're going to put an ancilla qubit at the center. You're going to initialize the ancilla qubit in a certain state. You do these C0 and C phase gates between the data qubits and the ancilla qubits, and then you measure the ancilla, and that tells you if there was an error or not. Now, if you look at how the stabilizers change, how the error syndrome changes with the Z errors, you'll see that Z errors gives you syndromes along the diagonals. So one Z error is going to give you this syndrome, and then 2 Z errors are going to be giving you these syndromes. And if you had an X error, then it's going to give you the syndrome along the other diagonal. So basically, the XZZX surface code looks like disjoint repetition codes. If you look at this, you can easily see that this basically looks like disjoint repetition codes for say the Z error, which is in our case the most dominant error, and it's also the disjoint repetition code. If you just had the X error, then it's the disjoint repetition code along the other diagonal. So it turns out that in this case, sorry, one more thing. So you could actually, as they mentioned in this paper as well, you could actually also rotate this lattice and get an equivalent lattice. And this is the same XZZX surface code, but in a rotated lattice. But now what you can do is you can have a rectangular lattice instead of a square lattice. And you can adjust these, the length and the height of the rectangle, depending on how many errors you want to correct. So the length sort of decides the distance or the number of Z errors you can correct, and the height decides the number of X errors or the distance of X errors. So if magically you did not have any X error, you magically had a bias of infinity, or like 10 to the 18 or something like that, then you don't need really any protection against X errors, and you can just do a repetition code, like a single line repetition code in this case. But of course, having that big of a bias is experimentally not possible. So, you know, there's, you can pick an optimum dx dz depending on how much bias you have in your system. Okay. Now, what they have shown is that for this XZZX code, you can that's pretty awesome. So we have increased, I mean, they have increased the threshold. The question though is, what happens when you take into account the circuit level noise? So this was under phenomenological noise, not under the circuit level noise. So phenomenological noise is you just put errors on your data qubits and just put measurement errors. So you've not put errors in the circuit level yet. So why is circuit level noise so different? Well, let's see. So remember, you were trying to use this circuit to measure the error syndrome. So this circuit uses, for example, a C-phase gate. So you do a ZZ gate between the datas and the ancilla. So if you have Z dominant error, then if there's a Z error on the data qubit during the gate, then it propagates as Z errors on the data qubit after the gate. And similarly, if you have a Z error on the ancilla qubit during the gate, then it propagates as a Z error on the ancilla qubit after the gate. So a Z error propagates as Z error, and the noise channel of the CS gate itself is biased. Now let's look at what are the other operations that this circuit is using. The circuit is using preparations and measurements, and these are also trivially biased. Now, the last thing that the circuit is using is a C-NOT gate. When you try to do a C-NOT gate between the data and the ancilla, you would try to engineer an interaction Hamiltonian, which looks like this for X tensor Z. So now if there is a Z error on the data qubit during the gate, then that Z error propagates actually as a linear combination of Z errors and Y errors on the data qubit. So now the gate itself has unbiased the error channel. It has converted the most dominant error in the ideal qubit to the less dominant one. So now the Y errors are sort of as likely as the Z errors, and so the noise channel is not biased anymore. So there was actually a no-go theorem, which was originally brought up in this paper by Alifers and Preskill, which showed that which did not show, but it proposed that you cannot do a native bias preserving C-NOT gate, that is a C-NOT gate which has a biased noise channel. You cannot do that in strictly two-level systems. So, well, then it seems that, you know, you would not really gain big advantage when you're taking into account circuit level noise, because now your circuit itself is unbiasing the channel. Well, fortunately, what you're going to see is that these Kerr-cat qubits, because of the continuous variable nature, you will be able to go around this no-go theorem and do a bias preserving C-NOT gate, but we'll come to that in a second. But before that, let's numerically see what is the difference between having a bias-preserving C0 gate versus not having a bias-preserving C0 gate? So what we did was we took Andrew's code and we looked at, the patch of the XZZX surface code and looked at the logical failure rate versus the gate infidelities for different sizes of the lattice. So here, suppose I assume that the C0 gate has a bias-preserving, it's a bias-preserving C0, so there's only Z errors. Magically, somebody gave me this. And I plot the error rate, and these lines cross at one point, and that's the threshold. Now, suppose I don't have this bias-preserving C0 gate, then, and if I choose a C0 gate in which the Z errors are being also converted to Y errors, then for the same, I do the same thing, and now I get another point of crossing. So in this case, the threshold is about 2%, and in this case, the threshold is about 1.6%. So having a bias-preserving C0 gate actually helps you to get a higher threshold. What is also important is to look at what is the logical error rate. So if you look at the C0 gate, here the failure probability is 1.4%. And for the same amount of failure probability when the gate was unbiased, but the total infidelity is still 1.4%, the logical error rates are different. So in this case, on the left side, the logical error rate is lower than on the right side. So again, you also gain in the logical, of course, as you should, you also gain in the logical error rate by just changing the structure of noise. So total noise is the same, but you're just changing the structure and you gain in both the thresholds and the logical error rate. So this comes back to this emphasizes message one, know your noise. Don't just use fidelity, be more clever, use the structure of noise as well. Okay, so now we come to the second part is this very special Kerr-cat qubit that I've been talking about. So this Kerr-cat qubit is made in it's a continuous variable bosonic qubit, but it's very strange because it's made actually in a transmon. It is made by driving a anharmonic oscillator, which is a transmon. So this is the Hamiltonian of the transmon, approximate Hamiltonian of the single Josephson junction or the transmon. So the first term is a frequency and the second term is a Kerr nonlinearity. Now what you do is you drive the system by two drives, which are equally read and beauty tuned from the center frequency. And now you'll get this 2-photon drive. So you'll take one photon from this drive, one photon from this drive, and convert it to 2 photons at omega q. Now, it turns out that you can also get this the same Hamiltonian in something called as a Snell device, which is a asymmetric loop made with 4 Josephson junctions, and you flux bias it so that you get both 3-wave and 4-wave mixing terms. And Nick is actually going to tell you about this more because that's where the Kerr-cat was actually made. And in this case, though, you can just apply a single drive at 2 omega q to get the 2-photon drive. So now what you can do is go in the rotating frame of omega q, and you get rid of these frequency terms, and you get this time-independent Hamiltonian. Now you can immediately factorize this Hamiltonian in this form, and I'm going to make a substitution that square root of this guy is alpha, so that the Hamiltonian looks like this. Now you can immediately see that there'll be 2 coherent states, plus and minus alpha, which are the degenerate eigenstates of the Hamiltonian. That means that they're also, that means that even in odd superposition states are also the degenerate eigenstates of the Hamiltonian. And these even in odd superposition states are our cat states, and these are going to be our qubits. Okay. So now we have our qubit, and this is the basis that this is a block sphere I'm going to be using. Fair warning, I think Nick is going to use a different block sphere, 90-degree rotated block sphere, so good luck. But this is what theorists like to use. So the cat plus and the cat minus states are going to be along the x-axis, and there's 2 positions, which are the coherent states, are going to be along the z-axis. Basic couples between the C minus and C plus states, and the poly X operator basically just puts a phase between the C plus and C minus states. So on the right hand side here, I have the Hilbert space structure of this Hamiltonian, and you see that the cat plus and cat minus states are the degenerate eigenstates, and they're separated from the rest of the Hilbert space by a large energy gap. The energy gap increases with the number of photons you put in and the nonlinearity. And this energy gap is what lets you, sorry, was there?
5 minutes till questions, that's it.
5 minutes to questions, okay. So I'm gonna go a little bit fast because I wanna show some results. So this energy gap is what lets you actually define a qubit, because now you can apply a drive and selectively cause transitions in the cat bases. So in our superconducting circuits, this energy gap can be very large. It's about 100 to 1,000 times faster than the typical decoherence times, which means that you can get really high fidelity operations. So you heard yesterday from Kyunji about the dissipative cats. And that the sort of fidelities you can achieve was limited by this the rate of 2-photon dissipation and the single photon loss rate, or the T1 time. Here it's limited by Kerr divided by the single photon loss rate, and this can be very, very large. It's like free almost, whereas here you have to do a lot of work to actually make kappa do larger than kappa. Okay, so now I want to show you that this is a bias noise qubit. For that, what I'm going to very, very quickly go through this because I want to show you the actual results from the surface code simulations. So this is a bias noise qubit. You can easily actually show that. Actually, let me skip this. Just believe me that this is a bias noise qubit. We have done a lot of theory in our paper to actually prove that it is a bias noise qubit for a general environment. So I'm going to skip all of that. Never mind. Maybe Nick will talk about some of this. So, okay, so I just wanted to show that you can do all the operations that you would ever want to build a surface code with this qubit. Some of these have been demonstrated, and Nick is working on the 2-qubit gates right now. I'm just gonna go all of that, and I'm just gonna show you this threshold work. So now, I didn't tell you that it was a bias noise qubit, but it is a bias noise qubit. I didn't tell you that how you could do the CNOT gate. Nick is going to tell you that, and he's also going to show you some experimental results. So just believe me when I say that. We have a bias preserving CNOT gate. So now we want to build the XZZX surface code with our snail-based Kerr-cat qubits. Oops. Yeah, so now what we're going to do is we simulated the same XZZ lattice, but now we simulated for real system parameters of our Kerr-cat. So what we do is we fix the parameters of the cavity, we fix the Kerr nonlinearity, we fix the loss rates, and we change the size of the cat. So on the left-hand side, we have the cat with size 1 photon, and on the right, we have cat with size 6 photons. And we simulate the different gates. We optimize the gates, and we simulate them. We simulate the CNOT gate, the C-phase gate, we simulate the measurements and preparations. And with the real master equation simulations, we extract the error channel and then plug that in into Andrew's XZZX surface code, and we get these numbers. So on the left, you see the logical error rates for different sizes of the lattice, and they all cross at one point, and so that is a threshold. And on the right, again, for the 6-photon cats, you get a threshold. So here the threshold is at the point of kappa over Kerr of about 1.2. What this means is that if the Kerr nonlinearity is about 10 megahertz, which is what is in our current system, then you need a kappa, 1 over kappa of about 132 microseconds. So you need an effective transmon lifetime of 132 microseconds. The current experiment, 1 over kappa is about 15 microseconds. So a factor of 10 away from where we need to be. Okay, so now if you look at on the right-hand side, there are 6 photons. Now the threshold is going to change. With 6 photons, you have a bigger bias. I forgot to tell you that the bias actually increases with the number of photons. So here, you get a higher threshold. The system can tolerate more loss. And here the threshold happens at kappa over Kerr of about 3, which means 1 over kappa, or the T1 lifetime of your transmon, to be about 64 microseconds. So now, really, it's not that much away. So basically what this is showing you is that if Nick just puts in a little bit more effort and makes a little bit better cavity, he'll already be below the threshold limit. What is also important is to actually look on the x-axis on the top. So if you look at on the x-axis on the top on the right, it shows you what is the corresponding fidelity of the gates at this point. So this shows you what is the threshold fidelity of the CNOT gate for this particular kappa, and that is about 6%. So really, it can tolerate a 6% infidelity of the CNOT gate, which is amazing. And it's a huge improvement. Okay, so this basically comes back to my message too, that fault tolerance with bosonic qubits is not only possible, but it can be much, much, much more efficient. You get much higher thresholds, you can tolerate more loss because you have structured noise. Okay, so I'm gonna leave you with this. So for the ongoing work we are doing, in the theory, we are doing work on magic state distillation and injection with my student Shraddha. And the idea is that now we want to use the bias in the qubits to actually make magic state injection and distillation much more efficient, reduce the overheads for that. And spoiler alert, we expect to get almost quadratic savings in the overheads. And we're also looking at doing gates and all of that. And in the experiment, of course, Nick is trying to demonstrate the C0 gate. And here is Nick very seriously trying to do his experiments even during the pandemic so that he can get the gate out to you. So I'm going to stop here.
Well, thank you very much, Shruti, for a wonderful talk. We have a couple minutes for questions, so don't be shy to post something in the chat. But while we wait for that, I did have a sort of question about the choice of the XZZX version of the surface code, because I've heard you talk about this before with the kind of version of the surface code where you think about using X and Y stabilizers if you primarily have Z noise. And I was wondering if you had something to say about why you might want to use the XZZX instead of that.
Right, so there are two reasons. First, I think that the decoding of the XZZX code is much, much easier. It's much, much better. The other important reason is that in the XZZX surface code, you're actually using only two C0 gates. The C0 gates are the hard one, and you're using two C-phase gates, which are free, essentially. So the fidelity of the C-phase gates is much higher than the fidelity of the C0 gate for the same amount of loss in the cavity, etc. So you already gain a lot. So like if in this last figure, I were to plot the corresponding C-phase gate fidelity on the top x-axis, it would be like 1% or something.
Okay, no, that's very interesting that it connects a lot to the specific hardware you're thinking about.
Yeah.
Yeah, well, that's good. Are there other questions for Shruti?
I just gave a great talk.
Yeah, left all the no questions lingering.
Yeah, I left all the hard part for Nick, so you can grill him.
So I have a question. I'll just unmute myself rather than typing. So I imagine that the numbers here are for like 3D architectures. Is that right?
Which numbers?
Well, like if you're comparing like your like whatever your noise sources are, this is probably for the best 3D architectures. Is that right?
No, it's not. So cap off 15 microseconds is like the worst it's like a really bad transmon.
Okay.
So routinely people have, I mean, like routinely, if you go to IBM, their transmons are like hundreds of microseconds. Even in academic labs, they're pretty long.
Sure.
So these are very, very conservative numbers. In fact, for example, when I put thermal photons in my simulations, I put a very high number for thermal photons. Okay. So this was the reason I put it was because this was in thermal photons that we were seeing in Nick's first experiment, but we don't expect that. There's no reason to expect that this is not going to go much, lower. Yeah. So this is like really conservative.
That's really cool.
Oh, we have another question. Baptiste asks, have you looked at the structure of the logical noise below threshold?
No. So is the question, I guess Baptiste is trying to ask if the logical noise itself is biased.
Yeah, biased or something.
Below threshold? I don't think so. That's interesting. I don't think so. I know Ben is on the chat if he wants to answer that. go ahead, Ben. But yeah, I don't think it should be biased.
All right. Oh, and I guess one last question. Leong asks, do you have an estimate of the typical size of the surface code for errors below threshold? For errors below threshold?
Oh, what do you mean typical size of the surface code for errors below threshold? You mean for reaching a particular target logical error rate, how big of a surface code would I need to have?
Yeah, he asks like if you went 10 times below threshold, how big of a surface code do you need?
Well, it has to be for a particular target logical error rate. So, okay, if you're asking me, say I'm going to factorize a 2000-bit number, how big of a lattice I need, I cannot tell that to you from these simulations. So one thing is that these simulations are done for periodic boundary conditions, not open boundary conditions. So we do expect the threshold things to be, the threshold is going to be the same for periodic and open boundary conditions, but the exact number that you want will depend on open boundary conditions. So I won't be able to give that to you right now.
Okay, well, I guess we could always discuss it during the break or later on if we need to. But for now, I guess thank you again, Shruti.